Hi everyone, welcome to the third lecture of the series on control of mechanical systems. In this lecture, we discuss the control of DC motors. We start with the mathematical modeling of DC motors, then we move on to the control of DC motors. DC motors are used as actuators in mechanical systems, and actuators basically transforms the control input signal into some force or torque input which drives the mechanical systems. The control input signal will be usually an electrical signal, and the DC motor takes that electrical voltage as an input, and it gives some mechanical output which is in the form of torque or force. In general, DC motors can be modeled as linear systems, and the dynamics can be represented either using time domain model, which is in the form of a linear state equation, or frequency domain model, which is in the form of a transfer function. Let's start with the time domain modeling, in which we consider a armature controlled DC motor as given in figure 1. Here, VA is the voltage applied to the armature, IA is the armature current, RA is the armature resistance, LA is the inductance of the armature, EB is the back EMF, T is the torque, omega is the angular velocity, J and B are the moment of inertia and the friction coefficient of the load. Now by applying voltage balance relation in the armature circuit, we obtain VA is equal to IA into RA plus LA into dIA by dt plus EB. And similarly, by applying torque balance in the mechanical circuit, we obtain TE is equal to J into d omega by dt plus B into omega plus TL, where TL is the load torque and TE is the torque developed by the motor. Now, by defining the state variable x1 equal to omega, which is the angular velocity, and x2 equal to IA, which is the armature current, and U is equal to VA, which is the armature voltage, and Y is equal to omega, we can obtain the state space model of the DC motor as in equation number 2, which is a second order linear state equation. Similarly, if we consider the state variable x1 equal to theta, which is the position of the DC motor, and x2 is equal to theta dot, which is omega, and x3 equal to IA, we can represent the DC motor as a state equation given in equation number 3. So here we have a model as a third order linear state equation. This state equation is used in the case of velocity control applications, and this one is used in the case of position control application. Therefore, based on the application, we can select the model of the DC motor. Next, we move on to the control of DC motors. So here we are considering the position control application of the DC motor. Therefore, we select the state space model of the DC motor as in equation number 4. So here x1 is the position. So the output equation will be like this, which gives y is equal to x1. And we define the control input using a linear state feedback control law as in equation number 5, in which xr is the reference state and x is the actual state, and k is the feedback gain. Now, in order to implement this control, we need to know the actual state, which can be estimated from the output and input data using a state observer. Now, for the DC motor, we are selecting the parameters as given here, which results in the system matrix and input matrix as given in equation number 6. The feedback gain matrix is chosen as in equation number 7. And in the simulation, we are considering two cases. The first one is the stabilization, in which the objective is to drive the system from a non-zero initial state to origin. And the second one is the set point tracking, in which the objective is to drive the system to a non-zero set point. Figure 2 shows the response of the DC motor for stabilization, in which we consider the initial state as 20, 10 and 5, and the objective is to drive the system from this initial state to origin. And from the plot we can see that the states are converging to 0 with the linear state feedback. And this plot shows the estimated state and the estimation error. From here we can see that the estimation error is converging to 0, which basically implies the observer is estimating the states accurately. And finally, this plot shows the control input with the linear state feedback control law. Figure 3 shows the response of the DC motor for the set point tracking case, and our objective is to change the position of the DC motor from 0 to 100. And we can see that the linear state feedback is able to achieve that. And this plot shows the response of the estimator, in which we can see that the estimated states are converging to actual states. And this also implies that the estimation error is converging to 0. And finally, this plot shows the control input in the case of linear state feedback. The MATLAB codes for these simulations can be downloaded from the link given in the description. That completes this lecture. Thanks for listening.